Okay, welcome to this give back for the IGCSE Physics, the Edexcel International GCSE. This is the November 2024 paper 1. Okay, so question 1, we have a planet, the moon. We're asked to draw the orbit of a comet, quite a common question. Make sure you've drawn it as an ellipse. And the star should be at the focus of the ellipse. Okay, there's two focuses of the ellipse. One sort of here, one at the other where I've drawn it. So something like that. Draw an arrow to show the force the planet exerts on the moon. So on the moon, directly towards the planet. This is a gravitational force. Okay, we're told then a time. We're asked for the speed. So speed is equal to distance divided by time, but the distance is obviously the circumference of a circle, and the time is the time period. So we're going to put in what units are meters per second. 2 times pi times 8.7 times 10 to the 10. Divided by 2.5 times 10 to the 8, puts that into your calculator, and you should get it's a two significant figure question. These are also two significant figures, so to two significant figures, it's 2,200 meters per second. Okay, then we have liquid water in this region around the sun. If the sun was replaced with a blue star, so you need to know, first thing you need to know is what is a blue star. So a blue star is hotter than the sun. You know that a blue Bunsen burner flame is hotter than a yellow Bunsen burner flame. So if the blue star is hotter, the liquid water would be further away, because where this liquid water is, where Earth is, would become hotter. So liquid water would be found further away from the star, something like that. Okay, question 2, an athlete, a sort of a mechanics-y question. So what we've got, kinetic energy equals half mv squared. I strongly suggest in the exam you don't use the shorthands like I have. You write this out in full. If you forget that speed should be v for velocity, you might lose a mark there very easily. So I really do suggest you write those out in full. Kinetic energy equals half mv squared. What do we have? Half times 85 times 4.5 squared. Put that into your calculator. Again, to two significant figures, because the question is to two significant figures. 860 joules. Maximum height, we have converted our GPE, our work done, into GPE. So state the increase in the amount of, we've got this much kinetic energy, we convert that into gravitational potential energy, so that's all converted into the gravitational potential energy. Look out for the buzzword state. That kind of means it's a really easy question. This just tell me the answer, you know the answer. It's the same answer as it was before. Okay, so GPE equals mass times gravitational field strength times height. Okay, now we're going to be working out the height is GPE divided by mg. We know that the GPE is 860. The mass, what's the mass, is 85 times 10. Put that in to your calculator and you get just over 1 meter. Again, two significant figures, 1.03 or something like this. Velocity time graph for the jump from the ground to the maximum jump. So when you launch off the ground at time 0, you're going at a very fast velocity. I say a very fast velocity, it's like sort of velocity 1.0 or whatever we just worked out, isn't it? You're going at that velocity. When you are at the top, you're going to be going at velocity equals 0. So this is going to be do it with a ruler, put a straight line, something like that. Probably wouldn't have those marks on the real thing, something like that, and the gradient of that. Oh, in fact, this is the next question. What feature of the velocity time graph gives the acceleration? It's the gradient. The gradient of the velocity line graph is an acceleration, which in this case is the acceleration due to gravity. Okay, that's the gradient would be 10. Why is the gravitational field strength different on the moon to the Earth? Don't use the word size, okay? Use the word mass. So the Earth has more mass than the moon. Okay, that keyword is mass. Second mark. I think you want to say gravitational field strength, G, is proportional to the mass of an object, something like that. You want to say, there's you've got more mass gives you more gravitational field strength, something like that. But don't use the word size. That's the main thing there. Okay, question 3, an electricity question, safety question. Plastic is an insulator. Okay, so it's going to keep us safe. What does it mean? It's going to prevent the user from getting a shock. So definitely use the word insulator and then say, what does that mean? Stops the electricity flowing, stops the current flowing, something like that, stops you getting a shock. Another mathsy one, PIV this time. We have a current equals power divided by V. We're told that the power is 350. You are expected to know, oh no, it doesn't tell you here that the voltage is 230, but 350 divided by 230, 1.5 amps. Okay, what your parents probably refer to as your fuse box doesn't actually have fuses in it. It has circuit breakers. Why? So a couple of reasons. First of all is as it is resettable. In other words, the fuse blows, as you might say in your house, and you can just turn it back on. So it's it can be used lots of times. And the other reason that it's used, and potentially the more important one from a safety point of view, as it is faster to turn off the circuit. Okay, a fuse can take a few seconds to melt. The circuit breaker can stop straight away. Okay, radioactive question here. What do we have? On the graph, give the unit for activity. Crikey, I can never spell this. It's becquerel. So it's capital B, lowercase q. That would be enough to get the marks, I believe. To spell it, BECQUEREL, becquerels. But capital B, lowercase q. What is meant by background radiation? So the radiation that is always around us. Right, you sat in your home now, or in a library or somewhere like that. Outside, even you are exposed to background radiation. It's around us all the time. I think for the second mark, let's give an example. So, for example, where does it come from? It comes from the sun would be a good example. Rocks, radon gas in the air, Okay, so a few different sources probably to pick up the second mark. Say a sensible one. What's half-life? Okay, the first mark for this, make sure you know this definition. The first mark is always saying for saying it's the time. Half-life is a time. It's measured in, well, presumably for this question here, it'll be measured in minutes. Taken for the activity to half. Use the graph to determine the half-life of this sample. Okay, so we start at 1,200. Get your ruler and draw over from 600. So 1,200 halved is 600. And that takes, what's the scale here? 16, 17, 18, right? That takes 19 minutes. So that's the half-life. You get 1 mark for doing the graph work, 1 mark for getting the answer. I'm sure there's a range probably allowed. If you wanted to double check that, you could go from 800 down to 400 or something like that, and you'd see that you'd get the same answer. I'm not going to do that today, but if you were, sat an exam and you really wanted to check something, you could. Right, okay, one of these questions. So take a few points from the graph. So I think it's probably good to make a little table here. So time, activity, and then constants. Make a little table and do it, I don't know, 3 or 4 times. So, at time 0, at time 5, at time 10, at time 15, whatever it is, take those readings from here and, read off the time, read off the activity. So I think the activity is 1,200 here, 1,000 here, at 10 minutes it was 840, at 15 it's 700. Pick your own readings, probably try and spread them out across the whole graph, and then do it. So activity times time, well, because you're timing it by 0, it's 0. 5 times 1,000 is 5,000. 10 times 840 is 8,400. Yeah, it's not looking good actually. This is at 15 times 700 is 10,500. So yeah, it's not true actually. No, okay. So I'm going to say this does not appear to be true, as the constant is changing. I think the key word I'm going to use is significantly. The constant, because I've read them off the graph, is going to move a little bit. But no, I've got 0, 5,000, 8,400, 10,500. They're significant differences. So yeah, that's not going to be true. Okay, we've got a north pole and a south pole. There's going to be a uniform magnetic field in here. Do these with your ruler in the exam. They should be equally spaced. They should be from north to south. Okay, here we go. Right, so we have the current going through here like this. We have magnetic field going across like that. The shorthand for magnetic field is B. The shorthand for current is I. Draw another arrow to show the direction of the force. Well, what you can't see is I'm doing my Fleming's left-hand rule. My current, my middle finger, is pointing directly away from me. The current is going from left to right. So my first finger, I can't draw hands to really help you out with this, but I've got my first finger, my pointing finger is going to the right from north to south. My middle finger is going away from me, and that is leaving my thumb pointing down. To be honest, all I'd probably leave on my paper is an arrow going vertically downwards. 2 marks for doing that. yeah, one mark for figuring out it's perpendicular, in other words, it's up or down, and 2 marks for getting it's downwards. Okay, here we go. Nice motor effects question. 4 marks. What is the easiest way to get the marks? So I think the first thing you're going to do is going to say there's a force on the wire. Which bits of the wire? Well, the force on wire AB, that's the wire we just spoke about, and CD. Specifically, we just did, what did we do? We just did BA, didn't we? So BA is going to feel a force downwards, CD is going to feel a force upwards, because the current is in opposite direction. So wires feel opposite forces, right? Because AB is the wire we just did, and then CD, the current's going in the opposite direction. So therefore, it's going to spin. So yeah, I should probably say that wires feel opposite forces because currents in opposite directions. Okay, and then oh, sorry, I've just read the question properly. Explain why the loop starts to turn. I've done that. What I need to do for the 4th mark is say, why does it stop when the loop is vertical? Well, what you'd get in a real life motor is a split ring commutator there, and there's not a split ring commutator there. So for the 4th and final mark, I'm going to say no split ring commutator means the coil will stop after a quarter of a turn. In other words, when it gets to the, BA gets to the bottom and CD gets to the top, it's going to stop. Question 6. Refraction. Lovely. Cracky. We've done a lot of writing questions here, haven't we? But here we go. Draw a diagram to do this. Probably words. I don't know. Let's start writing some stuff. I mean, you hopefully remember this experiment from school. What are we gonna? Yeah, try 5 marks. Oh dear. Okay, so draw round block. I am gonna draw this just so they can see. I understand that, that's my normal, that's my 10-degree line, that's my 20-degree line, that's my 30-degree line, etc. Just so I can sort of show them that I do know what my angle of incidence is. Draw a round block, measure rays of incidence to shine light ray along something like this. Measure angle of refraction with protractor. Do for multiple angles of instance. I'm doing it for 10 degrees, 20 degrees, 30 degrees, so on. How many marks is this? 5, okay. So tell them how am I going to work out. Yeah, okay, they've told me that in the question, haven't they? So I was going to say that, but I'm going to say do a graph of plots sine I against sine R, and then I'm going to say the gradient is refractive index, or 1 over the gradient, depending on which way around you plot your axes. Something like that. I've said 6 points. Hopefully I've got my 5 marks there. Right, weird question is because they tell me the equation there and then they ask for it, but that's okay. calculate. Oh, sorry, that was probably a clue. That was a clue that I was doing something wrong, wasn't it? Ignore what I just said. It's about critical angle. So critical angle equals inverse sine 1 over n, inverse sine 1 over 1.2. And when you put that into your calculator, make sure you're in degrees mode. If you've encountered radians, you get 56 degrees. What is meant by total internal reflection? 3 marks. All light is reflected. In other words, it stays inside the medium. It only happens when you travel from a high refractive index material to a low refractive index material. And it also happens when angle of incidence is greater than the critical angle. Okay. Oh my life, you've got to use a protractor here. So use a protractor to determine the angle of incidence at the point. Right, in other words, you're measuring this angle there. Okay, do that with a protractor, and hopefully you will get 24 degrees. Complete the path of the ray. Now, we know that the critical angle is 56 degrees. Now, because 24 degrees is less than 56 degrees, we're not going to get total internal reflection. We're going to get refraction. Okay, so it should bend out here, and your angle of refraction, because we're going from glass into air, should be larger than the angle of incidence. Okay, if 24 was larger than the critical angle, it would do a total internal reflection, but that's not the case. That's not the case for this. Okay, submarine. We have upthrust, and of course we have weight. If you're on Earth, you've always got weight. It doesn't matter if you're underwater, you've still got weight. Okay, draw these arrows. We have weight. We have upthrust. Can I draw that as U? Yeah, something like that. They should be the same. Yeah, at rest, they're the same size. What is the equation linking pressure difference, change in pressure, equals rho G H? Calculate the pressure from the water. Okay, yeah, that's right. So the pressure difference, that's just a complicated word, then pressure difference. Rho G H equals 1030 times 10 times 38. Put that into your calculator and you end up with 390 kilopascals. 390 kilopascals. Be careful with your prefixes there. It's 390,000 pascals, 390 kilopascals. To bring ourselves back up to the surface, we pump air in. How does air exert pressure on the walls of the storage tank? I'm tempted to sort of draw a diagram. You've got obviously your gas moving around like this. So the first mark is going to be there are collisions between particles and the walls of the container. Okay, when this happens, the particles exert force on the walls, and pressure equals force divided by area, i.e. force leads to pressure. The air in the storage tank starts at a pressure 410, and we have have a temperature change. So we have a P1 over T1 equals P2 over T2. So that is pressure 1. Pressure 2 is what we're trying to work out. So 410 equals actually P2. I'm going to keep it in kilopascals because the answer's in kilopascals, so I'm going to keep it in kilopascals. That is T1 and that is T2, but you need to be careful because it's not 2.5, it's 2.5 plus 273 because we need to be in Kelvin. And this needs to be 18 plus 273. So pressure 2 is going to be equal to 410 divided by 275.5 multiplied by 291. And you put that into your calculator and you get 430. Again, be careful about units, I mean kilopascals. Two whales communicate with sounds. Right, okay. I would honestly not use a diagram for this one. I would just make sure you know what the definitions are. Transverse waves, oscillates perpendicular to wave motion. Okay, longitudinal waves oscillates parallel to wave motion. I will make a diagram seeing as it said we could. So a transverse wave looks something like that. Longitudinal waves, difficult to draw. Something like that maybe. Best drawing in the world. Find a better version in your textbook. Something like that. Whale A makes a sound with constant frequency. The sound is detected by whale B. Doppler effect. Explain how the Doppler effect causes the frequency of sounds to increase. Okay, this is quite a tricky one to explain. So sorry, which one's moving? Whale A is moving. So the point is whale A is moving. So whale A is making a sound here. So it's making a sound here that looks, the wavefront looks like that. But a few seconds ago it was there, its mouth was there. And again, it made a sound that has now had a chance to spread out. So it's a circle centered around that point, but it's a bigger circle because it happened longer ago, and a bit before there, it was at that point there, and again, it would have made a circle. So that's what you have to try and explain, which is tricky. I'd actually be tempted to leave something like that on my answer and sort of see previous diagram. At least I can then tell the examiner I do know what I'm talking about. But anyway, let's try and get some marks. So the wavefronts get closer together. Okay, in the direction that we're talking about, the wavefronts have got close together. The speed of sounds stays the same. This leads to higher frequency heard by whale B. Visible light from the sun. It's just a plug it straight in equation. V equals F lambda. So 3 times 10 to the 8 divided by the wavelength is 5.4 times 10 to the minus 7 plug that into your calculator and you should get 5.6 times 10 to 14 hertz. Make sure you know how to use standard form. Okay, how the voltage of a diode affects currents. Right, okay, so we need to know the voltage of this diode. We need, say, diode we've done, the voltmeter we've done. We also need to know the currents through it. Ammeter we've done the wires, obviously. And that is going to be going up to cell. Current goes from positive to negative. Diode is also an arrow, so it should probably be that way around the cell. Although I'm not sure that's going to matter too much. Cell, and then to control the voltage that we're giving the diode, we have a variable resistor, something like that for 4 marks. In the second investigation, calculate the current in the battery. Well, we've got 0.15, 0.23. They come together. So the question is, you've got to add those two together. 0.38 amps. Ohm's law. Resistance of resistor A. So R equals V divided by I. V is 2.9. The current is 0.15. Put that into your calculator and it comes to 19 ohms. Nice guessable mark later on in the exam. Okay, we've now got a series circuit. Oh, blimey. Resistor B has, so that's 19 ohms. That's 13 ohms. So our current is going to be V divided by R, 2.9 divided by our total resistance is now 32. So our current now is 0.09 amps. In other words, much lower than whatever it was here, 0.38. So not quite what I'm going to say. So the new resistance, so I think I'm just going to say what I've done. So the new resistance is 32 ohms. New current equals 0.09 amps. Okay, so larger resistance, so they call it circuit 2 in diagram 2. So lower current. Conduction, again, hopefully something you've probably seen in school. We've got a heater, got all these metals, a bit of Vaseline on the end of it, and some sort of pin, coin or something like this. Independent variable, what do you change? You're changing the metal. I change the independent variable, the metal and material. What is the dependent variable? This is what you measure. You measure the time. Teacher tells student that their investigation is not valid. 2 ways to improve the validity. What's wrong with that? Yeah, okay, these distances are not the same, are they? This is much longer than this, so I think that's probably the first thing to do. So get rods the same length. What's wrong with that? I. Oh, and the sorry, the iron is also, this is thicker. Yeah, okay. The rod's the same length. That's rods the same diameter. Something like this. Student improves the validity. Describe what the students do to improve reliability. So reliability is all about, if you repeat it, do you get the same answers? So reliability is all about repeats, but taking a repeat does not improve the validity. It is, however, the first mark. You take the repeat, and then why do you take the repeat? You do that in order to remove anomalies, so you can remove the dodgy results, and then you can take an average. So you're taking an average of good results. That's going to improve the reliability. Okay, so just saying repeat here is probably just going to get you the first mark. Okay, here we go. Bar charts. So what have we got? Metal. Oh, right. Metal. Time. Seconds. There's always should be a nice scale here for 50, 100, 150 to, yeah, okay, so 50. Obviously do this with a bit more care than I'm doing now. 200s, 250, iron 180. What we got? 180. Oh my days, sorry. 60, 70, 80. Steel 230, 200s. Yeah, as I said, do this with a bit more care than what I'm doing. Aluminium, sorry, 140. Almost certainly lose some marks with this just being so messy in the exam, but hopefully you know how to plot a graph by this point. Okay, something like this. Why have we used a bar graph, not a line graph? Because the variables are discrete. Okay, you'd use a line graph if it's, say, a number and it's a continuous variable. Material is a discrete variable. You know, you're either iron or you are steel. You can't be halfway between them. Yes, I know you've learned about alloys in chemistry, but we're not going to worry about that for this. Right, stars are where nuclear fusion happens. What have we got to do here? We've got to figure out what's going on here. So this looks like the end of life of a star. So we're going to run out of hydrogen, and then we're going to turn into a red supergiant as we start to sort of run out of fuel. This is where we're going to start to make some heavier stuff. Then eventually it's going to blow up in a big supernova and turn into a black hole. And that's the end of the paper.